Hey everyone, I'm Steve Colenso with the Air Force Research Lab, and I, along with other members of the Air Force, the U.S. Space Force, and many other partners, make up the Hackasat team. In this video, we're going to give you an overview of Hackasat, some of our qualification challenges from our Hackasat 3 Qual event. We're going to talk about the Hackasat 3 final event, and where you're going to be able to view the digital twin demo that we gave at DEF CON 30 in the Aerospace Village. We're also going to show you the Moonlighter satellite that will be launching early in 2023. With me here is Eli Williams from the Space Systems Command. Eli, can you give us a little bit about what the mission is of Hackasat?
All right, thanks, Steve. Our mission is to inspire the world's top cybersecurity talent to develop the skills and awareness necessary to help build more secure space systems and reduce vulnerabilities. Consider it a global alliance of hackers, researchers, and enthusiasts working together to secure the future of space that we all depend on for daily life. We strive to host the world's best space capture the flag competition that involve solving complex problems that are relevant to space vehicles, the ground stations, and the links in between. When we aren't in competition mode, we continue to help our followers learn space faster with hopes of bridging the gap between space and cyber.
Over the past 2 years, Hackasat has garnered over 10,000 international competitors and millions of spectators from industry, academia, government, and the press. The Hackasat CTF has been held on everything from specialized space hardware on air-bearing tables to CubeSat form factor systems, creating space-relevant environments that gave access to a unique and novel experience for competitors. Hackasat has changed the way the globe looks at cybersecurity in space and how satellite designers and developers go about building security into their systems. Eli, what's the future hold for Hackasat?
Okay, this October, we have our final event for Hackasat 3, where the top 8 teams from this year's qualifications will take their shot at winning over $100,000 in cash prizes. Looking into next year, our biggest yet, we're going to be launching our space vehicle called Moonlighter. It's going to be on orbit, the first CTF in space. Moonlighter is set to launch in March 2023, and we will host the Hackasat 4 final event on this platform as the first on-orbit competition. Thanks, Steve.
So for the Hackasat 3 qualification event, which was a Jeopardy-style event held on May 21st and 22nd, that was approximately 32 hours long, there were 27 challenges over 7 categories ranging from space math to cryptology. We had over 800 teams and about 2,500 individuals participate. The top 10 winning teams received $10,000 each, and the top 40 teams received prize packs that had t-shirts, stickers, and coins. As you can see here, there were a number of challenges that were very difficult just by looking at the number of solves. The larger piece of the pie shows the easier challenges, and as we moved throughout the competition, we had some very difficult ones that only got a few solves. Mike Walker from our development team is going to walk through 2 of our more difficult challenges called Welcome to the Spider-Verse and Don't Fly Me to the Moon. All yours, Mike.
Hey, this is Mike Walker. I'm a principal software engineer at Cromulence, and my handle during Hackasat is Cydonia. Today, I'll be going over the Don't Fly Me to the Moon challenge that we ran during this year's Hackasat 3 qualification round. This challenge was inspired by real-life events. In January of this year, Bill Gray and several other astronomers who were tracking objects in Earth's orbit realized that there was an unknown object that would hit the moon in early March. There was initially some confusion over what exactly this object was. Initially, the astronomers thought this object was the upper stage of a SpaceX booster that was from several years ago, inserting a satellite into geosynchronous orbit. Later, they updated their findings to, suggest that maybe this was a Chinese launch rocket booster. Regardless of the origin, it's really standard procedure and extremely common for people and launch vehicles to be abandoned in upper orbit. There's not a lot of fuel to bring them back, and it's something that's pretty regularly done. So it's not unusual or even strange that somebody might have lost track of this booster. In March of this year, as predicted, This object smashed into the backside of the moon. The impact crater was even confirmed several months later by NASA's Lunar Reconnaissance Orbiter. And when this story hit the news, we thought this would make a great advanced level space math challenge. Here's how we presented the problem. The challenge prompt introduces the problem, and there's a really big hint in the prompt. It tells you you're working for the Galactic Mining and Tunneling Corporation, and specifically says that its acronym is GMAT. It's good to be inquisitive during these CTF events. So, if you were to just Google GMAT and space, you'd find that this references a free tool that does orbit planning provided by NASA, and that this tool is easy to install and comes with several tutorials on mission planning. It's highly advised that you use a tool like this when solving this problem. Otherwise, you'd have a lot of issues. When you log into the challenge itself, you can see it gives you the orbital parameters that Bill Gray and his team released in January, and then simply asks you for a timed list of maneuvers with an upper limit of 2 kilometers a second of delta V, which is quite a bit. Before we jump into the solution, let's talk just about the statistics overview for this challenge. Only 4 solves occurred on this. It was a very hard problem. I would rate this even at the graduate level. Engineering graduate students would try to solve this for a homework problem. And you can see the fastest team solved it in 4 hours, and we even had teams that took over 12 hours to solve it. So congratulations to all the teams that solved this. You really solved an advanced, very hard orbital mechanics problem. One that would easily be given as a homework assignment at the graduate level. All right, so let's talk about the solution to this problem. There's a few complexities that we need to acknowledge and account for in order to properly solve this problem. The first is that we're dealing in what's called the N-body problem. There's multiple gravitational bodies in the solar system, hundreds of them actually, but the primary ones we're concerned about in this problem are the Earth, the Moon, and the Sun. In past Hackasats, you could get away with using Keplerian orbital mechanics or just using the NASA two-line elements. But in this one, you needed to account for the Sun, the Earth, and the Moon at a minimum to solve the problem. And you could actually verify this if you set up the problem in GMAT or whatever tool you were using. The object in question, the booster, won't hit the Moon unless you turn on gravity for all of these bodies. And if you're not replicating what we said would happen, the booster doesn't hit the Moon, you're not going to have a chance to really solve this problem without first replicating, the problem itself. A couple things to note: there's no closed form solutions to the N-body problem. So, like we said, Keplerian orbital mechanics won't work here. Also, the Moon's orbit is elliptical, so even generalizations like the circularly restricted 3-body problem won't suffice. But it turns out space agencies and companies solve this type of problem all the time. You can solve this problem using a method called a 2-point boundary value problem solver. We know what the dynamics are. The solution is in closed form, but it's a numerical method to solve the trajectory because we know 2 points. So we're going to be using a 2-point boundary value problem solver, and GMAT actually comes with several tutorials that teach you how to use this tool. So let's take a look at the initial orbit. You can see in green, we have the booster. The Moon is gray, and the L4 point, which is where we're trying to bring the booster to, is in purple. What we're going to see as we go through this trajectory is that the booster will complete 2 orbits. It'll go through apoapsis twice. And right after the second apoapsis, it's going to smash into the back of the Moon. So we can see here it's gone through the first apoapsis, which is the highest point in the orbit. It's going to swing back by the Earth, and you'll see that the orbit has changed. It's no longer Keplerian because it came too close to the Moon. The Moon's gravity changed the orbit. So the orbit's changed. You're in a different orbit now. We're going to hit the second apoapsis the second time it hits its highest point in the orbit, and then in just a few seconds here, we're going to smash into the Moon just as Bill Gray predicted. There's the lunar impact. So here we have a basic cartoon of the Earth and the Moon, and we're going to talk about our problem in 3 simple steps in this cartoon to sort of plan out what we want to do before we go implement it in GMAT. Step 1 is we're going to drift to the second apoapsis, which is the highest point in our orbit. Step 2 is once we get there, we're going to use the 2-point boundary value problem solver to solve a burn that will take us to Earth Moon L4. Once we get to L4, we're going to solve a burn that makes our velocity 0 with respect to L4. Lagrange points are like L4 are equilibrium points in the Earth-Moon circular restricted three-body problem. And if you're exactly on that point, you'll stay there. L4 and L5 specifically are marginally stable points, which means if you get close to them, you'll stay close to them, at least in the circular restricted three-body problem. Now, we said we aren't in that problem. We have more than just the Earth and the Moon, but we'll see that this approximation will hold up at least for a basic solve to this problem. All right, so let's talk about using GMAT. For step one, we're going to set up the initial conditions in GMAT. We're going to turn on gravity for all bodies. You only need to do it for the Earth, Moon, and Sun to solve this. But we just turned it on in our solver for everything, like even Pluto, which has almost no effect. We just turned everything on. We're then going to propagate to the second apoapsis. So you can see the first two steps of the mission sequence are to go to apoapsis 1 and 2. Then we set up a targeting maneuver, which is the 2-point boundary value problem solver. And we allow that to vary our time of flight and our delta V along each axis. So that's four coefficients that can vary: time of flight, delta V in the x-axis, delta V in the y-axis, delta V in the z-axis. And then we tell it to achieve or to target x equals y equals 0 in the new L4 frame. So, we know we want to go to L4. We want our position to be 0 with respect to that. So we're going to try and hit that. Then step 3 is an easier solve. Once we get to that L4 point, we're going to use the same targeting 2-point boundary value problem solver to vary delta V. And all we're trying to achieve here is that our velocity with respect to L4 is 0. So it takes much longer to learn how to use this and solve all this. I just blew through the answer. But it really is, once you know what to do, it's that straightforward. So let's take a look at our solve in GMAT. You can see this is the same sort of video we saw before. Our booster is going through the first apoapsis. It's going to go to the second one, and then you'll see the trajectory will turn orange as we do our burn and go to L4. And then you'll see when we get to L4 that we do another burn and we stay there. So let's just wait for that to happen. All right, so you can see we're getting close to L4. We just hit it. And now you can see that our booster is actually tracking with L4. But as we go around to full lunar orbit, you'll see it slowly starting to drift away, right? Now you might be asking, I thought you said L4 is stable, right? Like if I go there, won't I stay there? And the answer is, if there was only the Earth and the Moon, and the Moon's orbit was a circle, yes, you would. But the Moon's orbit isn't a circle; it's an ellipse. And there are other bodies, specifically the Sun, that are perturbing that orbit. So you can see we stay close to L4, but we don't stay exactly there. So that's it for the solution. That was sufficient to stay close enough to L4 to solve this problem and get the flag. So yeah, congratulations to the teams that solved this challenge. Single event upset, PSLV, Delta Lays, and NSL. You all did a great job, and you did great at Space Math. Congratulations. The next challenge we're going to talk about is Welcome to the Spider-Verse. This was one of the advanced cryptography problems. So just like Don't Fly Me to the Moon, this problem had some inspiration in real life. Several years ago, some researchers discovered an unpatchable vulnerability in the Xilinx 7 series FPGA. And that FPGA just happens to be extremely common in spacecraft, but also everywhere. You can even see NASA's state-of-the-art spacecraft avionics board uses this sort of FPGA and is susceptible to this vulnerability. We called the problem Welcome to the Spider-Verse because in the paper and the video and several news articles about this vulnerability, it was referred to as a Spider-Man versus Spider-Man sort of problem. You use an FPGA to break its own encryption algorithm. So they called it that. So if you did a little web search, you would sort of get the joke that it's a Spider-Man versus Spider-Man problem, which is why you're in the Spider-Verse. So here's the challenge itself as we presented it. The challenge came with a markdown file that described a fake or a toy FPGA. We didn't want to give you a real Xilinx 7 because solving this problem is hard enough without having to read through pages and pages of Xilinx documentation. So we sort of dumbed it down to just the information you needed to solve it. And then we gave you an encrypted bit file for you to crack. If you were to feed this bit file into the challenge, what you'd see is that it prints the first 4 bytes of the flag and then exits. So you can kind of see whatever is encrypted in there is used to print the flag, but it's only printing 4 bytes. So in general, your task was to decrypt this file, change whatever is printing 4 bytes to printing the whole flag, and then to re-encrypt the file and have it be sent out. And just as a joke, we said that the encryption algorithm in the FPGA is definitely implemented in a very secure way. I'm not sure I believe that. I don't think anybody else did either. So before we get into the solution, let's just talk about the problem statistics. Only 3 teams solved this problem. So congratulations to Poland Into Space, Perfect Blue, and 1064 Bread. Pretty hard problem, and you all solved it. I know there was another team that had a solution but solved it after quals ended. So congratulations to you guys as well, even though you didn't score any points on it. Great job sticking with it and solving it. This is a real vulnerability in school that you were able to exploit it. All right, so based on the challenge description and a web search, we can basically determine very easily that this is an FPGA vulnerable to a Starbleed style attack, as described in the paper those researchers wrote. And that paper describes the attack in detail, and we'll do an overview of it today as well. FPGAs vulnerable to Starbleed have two critical components that are vulnerable, and together they allow this Starbleed style attack. The first is that their configuration engine has at least one register used for multi-boot logic, and unlike all the other configuration engine registers, this register is not cleared on FPGA reset or fallback, which means that if a security reset occurs, whatever is in that register will still be there after the reset. The second is that the FPGA improperly has implemented HMAC authentication, and it uses unencrypted data before it's authenticated. What that means is that we can conduct the following sort of attack, which is a Starbleed attack. The first thing you do is you can manipulate an encrypted bit stream given some known plain text and CBC malleability. When you do this, you do it so that you cause a write to occur to one of these multi-boot registers. The FPGA will then reset, and then after the FPGA resets, whatever unencrypted word you have in that register will be sitting there waiting for you unencrypted, and then you can use the same technique to cause a read to occur from that same multi-boot register, and one word at a time, you can repeat this attack for the entire encrypted section of your file. And use the FPGA as a decryption oracle. So let's take a look at the format of the bit stream that we gave you, the fake bit stream. There's some unencrypted sections, but mainly it's just a header and a footer and an encryption command. This fake FPGA doesn't allow any decrypted commands because we actually wanted you to decrypt and encrypt this file. So at first you might think, well, we don't know very much. But if you read through that markdown carefully, what you'll see is while data is encrypted, we actually know an awful lot about it. The stuff in yellow is encrypted data where we don't know what the plain text is, but we know what function it serves. So we know that there's an AES-256 initialization variable. We know there's an HMAC key. We know that there's an HMAC tag. And the green actually in this diagram shows that not only do we know what it's supposed to be, a write configuration command, we know both the plain text and the ciphertext. So this green highlighted word, this write configuration register, that's the crux of our attack. So if we look at the ciphertext again in terms of AES blocks, we know this sort of green word, as we said before, and we're going to conduct an AES or CBC malleability attack against this word to change the write to config to write to one of our multi-boot registers. So what are we going to do? We're going to modify the same word, but in the previous block. That's how a CBC malleability attack works. So we're going to modify the ciphertext so that we can change the plain text in the next block from OX01010004 to OX01 07, 00, and then I'm going to say XX, or the final two X's are the number of bytes we want to write. We're going to vary that XX from 48 to 64. And what this will do is it'll write 4 bytes at a time into our multi-boot register, with the last 4 bytes being the last word, the last 4 bytes being the bytes that remain after reset. We're going to use 48 to 64 bytes, so it'll be 4 writes. And what that will do is conduct an attack where we're decrypting the words in block 6 and writing them out to the multi-boot register. So if we do that attack against block 6, and we do it 4 times, once for each word in the block, then we'll have decrypted block 6. So once we do that, we'll have decrypted 1 block of all of the encrypted blocks we need. But we can conduct the same attack against block 6 to decrypt the rest of the blocks as well, simply by copying the block we want to decrypt and the block before it into block 6 and block 5 respectively. So if we want to decrypt block 2, we'd copy block 2 into block 6, block 1 into block 5, and then we'd carry out the same attack. And we do that for every single ciphertext block, and that'll allow us to decrypt the entire file without ever knowing the AES key. All right, once the file is decrypted, we can see everything that we've decrypted. So let's take a look at the decryption section of the file. You can see we have the HMAC key in there, and it's a bit of a joke. It's a very secure key. If you looked at this, you'd know for sure you decrypted it, right? Because it's like, haha, funny joke, not laughing at all. You can see there's the write config command we expect just in the spot the markdown file says it'll be. And then the first command after that, which we didn't know anything about, is a write command to register 3, and it's saying to write 18 bytes of data, and then it's followed by the data that is going to be written. And what you can see, if you look at the decoded text, is it's just a simple JSON string. So you can see it says print flag, and then it tells you a 4. And if you remember at the beginning of this challenge, your file printed out 4 bytes of the flag. So it's pretty obvious that what you need to do is change that 4 to a 999. However, once you do that, you'll have invalidated your HMAC tag. So you also need to change the HMAC tag, which is highlighted in green at the bottom, and change that as well to the new value. And if you wanted, you could even change the HMAC key to any arbitrary key you wanted. Since the HMAC key is encrypted, and in the encrypted section, that means we have the authority to change it to whatever we want. All right, so once we've changed those values, we then need to re-encrypt the file. And we're not going to go over how to do that in detail just for the sake of time. But both the paper that describes Starbleed and this other paper we referenced by Rizzo describe how to do that using CDC malleability and a decryption oracle. So since you already know how to decrypt a block of ciphertext, you can use the method described in these papers with CDC malleability to then re-encrypt the changes you made and get an encrypted bit file with your changes. You can then send that to the challenge server, and it'll print out the whole flag for you. So just to recap, what did we do? We used CDC malleability and Starbleed to create a decryption oracle. We used that decryption oracle to decrypt a bitstream file. We then forged a new bitstream with valid HMAC tags, but changed data. While we just changed data in this toy example to print out more of the flag, somebody could use this to implement hardware trojans in an FPGA and then make that bitstream file have valid HMAC tags. After that, we re-encrypted the forged bitstream with the decryption oracle, and we had a fully encrypted new file with forged data in it that is valid. And we did all of this without ever having the keys. We just did it with the FPGA itself. And just as a reminder, all Xilinx Series 7 FPGAs are vulnerable to this attack. Both the paper that we learned about this attack from and Xilinx have talked about countermeasures to this if you're using one of these. So if you are, I highly recommend you look into what they recommend. There are things you can do in hardware to stomp this attack out. And, aside from that, feel free to come back to this challenge and use it to practice your skills. And if you have a Xilinx 7 Series FPGA, maybe even try it out yourself. All right, thank you.
Thanks, Mike. That was a great amount of detail that now anyone can watch this video of and further research on the types of challenges. Next, we have our resident CTF expert, Jordan Wise, who's going to go in depth about our Hackasat 3 final event.
Hackasat 3 has all eyes looking upward as we continue on the path toward a CTF in space. If you've been following along our journey, you might remember that in Hackasat 1, all teams were racing through challenges independently. In Year 2, we first introduced competitive aspects where teams could attack and defend their platform against their foes. And now, in Year 3, we're continuing that trend and moving to a pure virtual platform so that we can focus our hardware efforts on the satellite that's being launched in preparation for Year 4. We'll talk in more detail shortly about this new virtual platform, but it uses Basilisk to more closely model actual constraints team will face next year in the real world. For example, in one of those constraints is that you have limited communication windows with a real satellite. They're not always overhead, and you have to coordinate your communications between ground stations to minimize periods where they're unavailable. We're also joined in the finals this year, Year 3, by both new and returning teams. Poland Cannon into Space, who scored second place in the finals last year and first place in qualifying last year, is back again with a first place qualifying finish, looking strong as usual. Perfect Blue came in second in the qualifiers this year, and that's not a surprise. They were actually the highest scoring CTF team worldwide last year on CTF time. Our third place qualifying team is the German Veltalis, who is also a returning team from last year's finals. Of course, our fourth place qualifier, the French team Solarwine, is still the one to beat, having not only been the top scorer in Year 1, but also the first place winner in the finals in Year 2. Unlike the other teams described beforehand, many of the CTF regulars that we've seen in other events, Solarwine came together just for Hackasat. And that's also true from our fifth place qualifying team, Single Event Upset, also back from last year. One of the other new teams to Hackasat this year is Team Organizers. And yes, that is going to make describing when they score and what happens in the game a little complicated, but it's worth the joke. It's not a surprise, of course, though, because currently on CTF time, they're actually second this year in the global rankings. New this year, but not new to the event, is Team Samurai, a long-standing CTF team that played in Year 1, didn't make it last year, but they're back in Year 3. Finally, Space Bits Are Us was our 8th place qualifying team and another first-timer. They placed 28th in quals last year, but with a great improvement, made it into the top 8 this year and made it into the money. And speaking of money, as a reminder, all those qualifying teams, plus 2 other alternates, Mhackaroni and PPP, all won $10,000 and a great prize pack for their performance beforehand. And even better, they're now competing for $50,000, $30,000, and $20,000 prizes in our final event, which will be broadcasting starting October 20th. Make sure you join us on hackasat.com and keep an eye on our Twitter at Hackasat, as we're looking forward to seeing you then as we watch these teams learn space.
Jordan, thanks for that. Hackasat 3 is shaping up to be quite the competition, and we are excited to watch it all play out. Now, Mike Wermeyer from our development team is going to take a look under the hood at the digital twin we've developed for Hackasat. Take it away, Mark.
Hey everyone, this is Mark Wermeyer, also handles Spacey McSpace from Quals earlier this year. I'm one of the engineers at Cromulence working on the digital twin for this year's finals. And today I'm going to give you a quick walkthrough of what we've put together so far as we approach finals. This is basically the system that we're putting together for teams to be able to compete with later this year. So just a quick overview of the architecture of the different pieces and tools that we brought together in the system. So one of the important things we brought in this year is a spacecraft simulation framework called Basilisk. This is from CU Boulder's ABS laboratory. And this allows us to do a lot of, manage a lot of the physics simulation. So manage the spacecraft orbits. We can put in things like star trackers and create telemetry from those devices. And we can send that telemetry onto flight software. So like we're using NASA's CFS and OpenSatKit to actually process that telemetry and make the spacecraft think it's in an actual orbit. So kind of it's broken into 2 halves. So on the left-hand side is more the infrastructure simulation side. This is more like what the admins would be looking at. So it has the Basilisk piece in there that's handling all the simulation elements. And then that sim data, while part of it's being passed to the spacecraft flight software, Also, parts of it are being passed to Grafana and Cesium.js, where we have some introspection into what the simulation is doing. And then Cesium.js allows us to get a 3D visualization, actually see the spacecraft in its orbit over the Earth, see where the attitude is pointing, see if the solar panels are pointed at the sun, get all that kind of information in a nice 3D visualization. On the right-hand side, so we've got our sensor data that's being passed into Core Flight's system. So this year we are running this on a RISC-V processor that we're emulating in QEMU. And that sensor data, so like our GPS receiver telemetry, positions, velocities, our star tracker attitudes, quaternions, how much power subsystems are consuming, how much power the solar panels are generating, and what's stored in the batteries. All that information is passed from Basilisk over to CFS and OpenSat-Kit and our RISC-V processor. So those pieces, that constitutes what we're calling the spacecraft in the game. And then from there, the spacecraft can be commanded and controlled from, so like a ground system sort of software like a satellite operator would use. This year we've migrated to Ball Aerospace's Cosmos 5. So this allows us to send commands up to that spacecraft so we can point it where we want. We can turn on and off subsystems. We can also view the telemetry coming back down. And so one difference between, so like when we're looking at sim data, we might be able to see all the attitude data and other physics data being generated. But then on the Cosmos side, we would only be able to see telemetry and send up commands when we have a connection established with the spacecraft. So, or if we turned off, for example, the star tracker, we'd no longer be able to see that star tracker telemetry in Cosmos, even though it's still being generated and handled over on the Basilisk side. A quick shout out to all the tools that we brought in. So like I said, Basilisk from CU Boulder's ABS laboratory, also Cesium.js, Core Flight System from NASA, Ball Aerospace's Cosmos, Grafana Linux on Lighttext, and OpenSat-Kit. So when I start up the digital twin, you're going to see these 4 screens. So just a quick explanation of what's happening. In the top left is our flight software. So this is where we have RISC-V emulated in QEMU, and on top of that, we're running our NASA Core Flight software apps and OpenSat-Kit, as well as our custom flight software that we've added in. And then on the right-hand side, the Cesium visualization. So this is where we can see where the spacecraft is in its orbit. We can actually move this visualization backwards and forwards in time. We can see if we're over ground stations. We can see what the spacecraft attitude is, if we're pointed at the sun. And the bottom left is the Grafana introspection into the simulation data that's being generated by Basilisk. So we'll be able to see the battery charge levels, what the solar panels are doing, what the devices are doing, how much power they're consuming, if we have any tumble rates on the spacecraft, and we can see all of that stuff there. And then in the bottom right is the Cosmos 5. This is sort of the satellite operator view. So this is where we can send up commands like a team would in finals, and also view telemetry. So now starting up the demo. So we've got all our 4 windows here. The first thing I'm going to do is start the flight software. So this is starting up Core Flight System. We've already got the RISC-V processor running, and you can see all of the CFS apps starting in that top left window. So basically, we've got our spacecraft started up, and now we should be able to send commands to it and receive telemetry from it. We've added in a gremlin for demonstration purposes here that's actually sending all of those actuator commands that you see in the flight software. So this is basically sending a bunch of rogue reaction wheel commands to cause the spacecraft to do a little tumble for us. So over on the Cesium visualization, here's our spacecraft. It's doing that commanded tumble. Also, we're over our Tribute Vegas ground station for DEF CON. And I'm just kind of showing here, you can just rotate around in the Cesium view. You can get a really good idea of what's happening. So for example, it's really hard to understand what your spacecraft is doing by just looking at, for example, quaternion values or Cartesian XYZ positions and velocity values. It's kind of hard to make sense of that. So putting it here in the visualization is a really good way to actually understand and sanity check what's happening. So down in the bottom left, we're looking at some of the simulation data that Grafana is graphing for us. So we can see because we have this tumble, we have a slowly declining battery charge rate, and as well we have this oscillating sort of behavior happening with the charge rate and also on the solar panels themselves. So as the spacecraft is tumbling, sometimes the solar panels are pointed at the sun and sometimes they're not. So that's why that's going up and down and why our battery charge rates are declining. Also here we have, this is a stack up of all of the subsystems and what they're consuming in terms of power. So we've also added another gremlin in here, which is randomly turning on and off different subsystems to demonstrate on the graph here. You can see that it's kind of shifting what subsystems are consuming power or how much power they're consuming. Moving further down, so here's our, this is our actual simulation position and velocity data and our attitude data. So we're tracking angular velocity, what the spacecraft's quaternion is. And up here we can see other things like our 3 reaction wheels, what speeds are they operating at. So like I said, the gremlin is sending these rogue reaction wheel commands, which is causing the reaction wheel to spin up. And then a couple other sensors here, you can see magnetometers, sun sensors. So moving over to the Cosmos side, we can see that we have a connection. Our Cosmos interface is connected with the spacecraft. We haven't sent or received any commands yet. So the first thing I'm going to do is I'm going to turn on telemetry for the spacecraft. So I'm commanding the spacecraft to start downlinking telemetry packets for me to view. Sending that command, and we should see it pop up in the top left. So there it says telemetry output has been enabled. So our core flight software has recognized that our command is now sending us telemetry. So here we see our received bytes count is increasing. So we're receiving those telemetry packets. And we can look here at a couple of different ones that we're receiving. So we're receiving core sun sensor, GPS, IMU packets. We open up the GPS packet. We can see in here that these values are updating as packets are coming in. So we have our CCSDS header to start with, and then lower down we have the actual GPS payload telemetry. So our Cartesian X values and velocity values. Another way to look at the telemetry, we built just a couple basic telemetry viewer screens. So this one shows what devices we're commanding to be on and off. So like I said, the gremlin that we're running is randomly turning on and off different ones. So like right now, the GPS just turned off, and then you should see that turn back on in a minute and something else will turn on. And then on the right, we have the GPS and star tracker telemetry. So those packets are actually being downlinked and Cosmos is parsing them. You can see that little gap in GPS telemetry while the GPS receiver was off, and then it turned back on and continued collecting telemetry. And now the star tracker just went off, so the star tracker telemetry is no longer updating. And then it should turn on back in a second here. There it goes. So now we're receiving those star tracker telemetry packets again. And just monitoring, the gremlins sending the rogue reaction wheel commands, so that's causing those star tracker telemetry quaternions to do those variations and rotations. So right now, what I'm doing to demonstrate what the flight software is doing, so I'm actually going to kill the core CPU1 process. So I've actually stopped the flight software, and now looking back in Cosmos, we can see we're no longer receiving any star tracker telemetry. Those graphs have just stopped at their last recorded values. So this would be like a satellite operator when you've gone out of, for example, you've gone out of contact with your spacecraft, you would no longer see these, you would just see whatever the last recorded values are for that telemetry. And further illustrating this, so our received bytes is no longer incrementing. So even though we've turned off the flight software, Basilisk is still simulating the spacecraft, it's still handling all the physics. So our spacecraft is still tumbling, our orbit, it's still propagating. We can see that happening in cesium, and we can see it in the Grafana windows as well. So these Grafana simulation values are still updating and still generating values for us, even though the flight software is not running and we're not collecting telemetry as a spacecraft operator. And then, so on power consumption, we've turned off the flight software, which also killed our gremlin that was turning on and off random subsystems. So the subsystems are just remaining in their previous state. They're no longer changing, turning on and off. All right, and that's it for the digital twin demo. So yeah, I hope you guys enjoyed this, and looking forward to getting teams to have a chance to actually use this in finals later this year. All right, thanks.
Thanks, Mark. That was a great explanation of our digital twin. Keep in mind that the digital twin never leaves the terrestrial world and wouldn't last a millisecond in space. Now we're going to take a look at how all the components of the digital twin manifest themselves into a space-hardened satellite. Hackasat 4 will be the first CTF in space, using the Moonlighter satellite as the competition platform. Aaron Myrick is going to take us through on what design considerations are being made in the development of a CubeSat, such as Moonlighter.
Hi everybody, I'm Aaron Myrick from the Aerospace Corporation, and I'm here to talk to you about Moonlighter. So first, before we start diving into what Moonlighter actually is, let's start a little bit with some CubeSat concept development. So when you want to put things into space, you need to figure out first, what do you want your a satellite to do? So do you want it to take pictures of things? Do you want it to take pictures of the Earth, take pictures of space? Good examples of both of those are Planet and the James Webb Space Telescope, which recently launched. Do you want to provide SATCOM to users on the ground? So Iridium, Starlink, OneWeb are all examples of companies that do such a thing. There are also vehicles that provide relay links, and these can be for tracking planes. The ADS-B system does that, or tracking ships. So AIS, the Automatic Identification System, does that. Or there's actually amateur radio operators that have launched vehicles to bounce ham signals off of vehicles. There's synthetic aperture radar, which the farmers and geological services, mining companies use that data. And then could be another instance where you may want to launch a vehicle that no one's really thought of. Maybe you want to create a cyber test bed in space to test out different capabilities for defending space systems from cyber attacks. Part of the key pieces of this that you're trying to understand is why you would do this in space versus on the ground. So for taking pictures of things, it provides a nice vantage point. You can have a good revisit rate. You don't have to put planes up in the sky over certain areas all the time. SATCOM, there's a nice benefit because you have an overhead view. You don't have problems that you have with communication on the ground, where you have an antenna that has to be fairly tall and unsightly to provide those types of signals. So the first part of this concept development is really understanding what your concept of operations is, or ConOps for your vehicle. So trying to understand what it is you actually want to do. And so from there you go into sort of sizing up all the other parts around your mission. So the first key component that you're really trying to understand is the payload, since that's what's providing the mission, so to speak, to the rest of your system. So really what you're driving here is how big it is, how much power does it use, what are your physical constraints of that system. Do you need to have high computing or onboard processing, or can you just get it all to the ground and let ground take care of it? So you're trying to understand how big the payload can be, how small can it be, and then you want to figure out, okay, so for this specific capability that I'm trying to provide, what's a good orbit that this would fit at? So low Earth orbit is ideally suited for something that's cheaper to get to. It has a high revisit rate. You don't have to deal with radiation as much. And then when you go up in your orbits to mid-Earth or geosynchronous, you have a longer overhead time, but you start dealing with things like radiation that you have to account for. And also you have to use different sensors because the magnetic field isn't as strong, so there's some trade-offs there. And then another big factor in determining how big your vehicle is ultimately going to be is the pointing requirements, or if you need to do orbit transfers, because those are big components that need to be accounted for. And so you put all that together and you end up with a certain ideal size for your vehicle. It could be 1U, could be 3U, could be 6U, and a U is 10 by 10 by 10 centimeters. So with me here, I have a 3U metal chassis. So 1U is just one of these cubes here. A 3U is about this size, so length of my arm. The next part about all this is we want to sort of fit it all into this little box here. And so you get all your notional components and you start laying them out in your structure to see, does this actually make sense? Does this fit? If it's a big change, things that just absolutely don't fit, then you'll probably have to go up a size. If it's close, that's when you start making trade-offs about what it is you really need to do. So what are your defining requirements there? And then after you did all that, then you go into thermal modeling. So this is it can get very complex here. And you're looking at your model orbit. So we determined that in the previous phase of this, your power draw of all your components and how you're intending to operate the vehicle. Now, the reason why you want to do thermal modeling very early on is because heat is hard to dissipate in orbit. And once you launch, you're stuck with what you got. You cannot change anything. So this is the phase where we need to understand, do we need to add heat pipes? Do we need to put down a different thermal paste to increase the contact of the subsystems? How big are those contact patches with the different subsystems? What materials are we using? That plays a huge role in being able to dissipate heat. What kind of screws you're using, how thick they are, what do your mounting posts look like, where are those located? This all plays a role here. And remember when I talked about the processing power, so if you have more processing, you're going to end up generating more heat. And this has a secondary effect in that if you have more processing, then you need more batteries if your mission needs to survive eclipse cycles. More batteries also mean more heat. So there's a lot of things that generate heat here, and the goal is usually to just get the heat to the outer panels, and then the surface area of those outer panels is really what drives the heat dissipation. So they're conductive panels, and they get heat out into the surrounding area. And then to close it all out, as far as CubeSat design, you have your link segment and your ground segment. These are both largely driven by what your concept of operations is. So your link segment consists of two parts. You have your uplink and your downlink. The uplink is usually very slow. Part of that is there's usually not a need or a desire to have a large antenna on board your vehicle. So to have higher uplink speed, you'll need a bigger antenna, or an antenna that draws more power. And this is usually not a requirement that people have to deal with. So bottom line is more uplink generally means more money, both from your ground power and also being able to have a structure that can support it on board your vehicle. Then there's your downlink requirements. So we're looking at where are you downlinking, how many sites you have, how often do you need to do it, how big are the things you're trying to downlink. These are all factors that play into that. And then there's your ground segment. And this is where you do the command and control of the vehicle. If there's any off-board processing that needs to be done, that's where you would end up doing it. This is where you task your vehicle to do things, and you disseminate your data from there. All right, so now as a thought experiment, let's work through this concept development. So let's create a satellite here. Let's call it Moonlighter. Why not? So Moonlighter, I think we should have a vehicle that is used to test and experiment with different cyber capabilities. And now this vehicle, I think, should have a day job. That way we're getting a little realistic here. We don't necessarily care about the day job now, but we'll figure that out later. So as part of this, that vehicle will need to be fully reprogrammable, because that's how you would do exercises and do experiments. You need to be able to recover from any different cyber activities that are going on. So this vehicle absolutely needs to be 100% fully reprogrammable, and probably have a bit of a beefy processor involved in it. So taking all that, a payload that's pretty ambiguous, a beefy processor, we can have a notional idea of fitting this in a 3U vehicle like this one. So we'll fill it out with representative components. We're absolutely going to need some batteries in here, some power distribution, some guidance, navigation, and control. Both sensors and actuators are good to have. Absolutely going to need a uplink and downlink radio, and probably some fault management to check our cyber activities that we're doing to make sure we're not harming the rest of the vehicle. And then let's work through some of the mechanical and thermal side of it. Some of the early analysis have shown us that some of the mission operations are going to have to be traded off with some of the recharging that's going to need to be involved. And that's not necessarily a bad thing, but that is, acceptable for this mission. So with that, that's the early stages of Moonlighter, and I'll kick it back to Steve.
Aaron, thanks for all of that information. There was a lot to unpack there. We can definitely see the tremendous amount of work that goes into the design and development of a satellite that needs to exist in such a harsh environment such as space. To close things out, Rachel and Kevin are going to show you how you can get involved in Hackasat, what we brought to DEF CON 30 in August, and how you can follow along during our Hackasat 3 finals. Over to you guys.
Now that you have all the ins and outs of Hackasat, it's time for you to get involved. First, let's cover the good stuff you may have missed at DEF CON. We had a super cool setup in the Aerospace Village. Folks were able to check out our FlatSat museum. We had flat sets that we used in Hackasat 1 and Hackasat 2, and our developers that brought it all to life were on hand to talk about them. People had the chance to get on our final CTF platform and play with the digital twin, see if they could spot vulnerabilities, and learn how to command a satellite. We had a mock satellite CTF demo where you could try your hand at space cybersecurity challenges, get a feel for how our challenges look, how to tackle them, and an opportunity to ask questions. All that and lots of stickers. We had a great time at DEF CON, and we missed anybody that wasn't able to join us there. Lucky for you, there's still ways to interact with our team. We're happy to talk all things Hackasat. Hackasat.com has ways to get in touch with us and so much more. Kevin, why don't you tell them all the good stuff there?
Definitely. Yeah, check out our website at hackasat.com. There you can find a host of resources, including the opportunity to try your hand at previous Hackasat challenges, or check out explainer videos on various space cybersecurity topics. You can also read up on the latest Hackasat news and listen to a variety of podcasts that we've been a part of. You'll also be able to relive the action from Hackasat 1 and Hackasat 2 by watching a collection of overviews and recaps from those competitions. Also, see if you can complete any or all of the missions that White Rabbit has cooked up for you. Remember to sign up for our emailing list and check us out on Twitter for the latest updates on all things Hackasat. And of course, don't forget to check out Hackasat 3 finals taking place this year on October 22nd through October 23rd, streaming live on our website, hackasat.com. On the website, we'll display a live scoreboard so you can see who's on top as 8 of the world's best CTF teams vie for a $100,000 prize pool. We'll also have an interactive visualization tool where you can check out what's happening on board each team's satellites. Are they tumbling out of control? Are they running low on power? Or are they having trouble communicating with their ground station? Our customized interactive visualization lets you observe which challenges these teams are currently facing throughout the competition. Also, to help guide you through what's going on, we're going to have expert commentary from our resident CTF veteran, Jordan Wines, so that you can get the inside scoop on what's going on inside the game. We'll also post the team's bios so that you can learn about the finalists, where they come from, and what motivates them to tackle the Hackasat challenge. And last but not least, keep an eye out for Hackasat 4 registration coming up in 2023. This last event in the Hackasat series promises to be the best yet, with teams battling it out in the world's first CTF in space.